Okay, so for this problem, we're going to go through and solve this 3x3 system using the eigenvector method. And again, that always begins with us finding the eigenvalues for the matrix. So once again, we're going to start off by going through and finding the determinant of our A minus lambda I. And we will use cofactor expansion for this. So we're going to have 2 minus lambda times the 2x2 determinant, 2 minus lambda, 3, negative 4, negative 5 minus lambda. And again, we're expanding across the top row here. So these are the numbers that we're using. So again, going back. Then we're going to have a minus 4 times subdeterminant 1, negative 3, 3, and negative 5 minus lambda. And then we're going to have plus 4 times subdeterminant 1, negative 3, 2 minus lambda, and negative 4. Now this works out to be the cubic polynomial, which is negative lambda cubed minus lambda squared minus 4 lambda minus 4. And that calculation is really, really long. So what I'm going to do instead of going through the calculation on video is just I worked it out on a separate whiteboard, and I'm just going to include a picture of that in the notes. But again, this is a long calculation. It's about 12 steps or so. So now we can take this polynomial and factor out a negative 1. So we get lambda cubed plus lambda squared plus 4 lambda plus 4. And we can actually factor this by grouping. We can take a lambda squared out of the first, leaving us with lambda plus 1, a 4 out of the last two numbers, and that gives us a lambda plus 1. And then we could factor out that lambda plus 1, and that leaves us with a nice convenient lambda squared plus 4. And again, this was equal to 0 the whole time because we are finding eigenvalues. So our first value of lambda 1, is equal to negative 1. And then lambda 2 and lambda 3 are both imaginary numbers. They're both negative 2i and positive 2i. And so for the next part of the problem, we'll go through and find the eigenvectors corresponding to these eigenvalues.